that has been something more like an exponential growth, and it is having perhaps even a larger impact on radiation measurements. And here's a favorite article of mine, published by some very renowned physicists. That includes Otto Frisch, who invented the Frisch grid, some of you may know from ion chambers. And they decided they needed an instrument to sort out the amplitude of pulses that were coming from their detectors. And what they built was this. This is a mechanical pulse height analyzer, where there is a board that has a series of grooves milled into it. And up in the upper left-hand corner is a plunger that's inside a solenoid whose windings receive the amplified pulse from a nuclear pulse amplifier. Teed up in front of the plunger is a ball bearing. And when a pulse comes through, the ball bearing is hit by the plunger. If it's a big pulse, it gets knocked over into this groove over here on the right-hand side. And if it's a small pulse, it only gets hit a little bit, and it falls into one of these grooves over on the left-hand side. A remarkable mechanical multi-channel analyzer, anticipating the world of electronic multi-channel analyzers. And it's interesting to read one of the conclusions. Well, first of all, it has some advantages here, as pointed out by these distinguished authors. Chiefly cheapness, that's certainly an advantage. You don't have to pay a lot of money for that device. And the information it contains is displayed as a histogram all the time. Real-time display. There are a few examples prior to this of the use of the idea of real-time data display. And here you have it. Its main disadvantage is low storage capacity, about 100 a channel, and at that point, the ball bearings roll off on the floor and it makes quite a mess. And slowness. Pulses are sorted at most at a rate of about 6 a second. Well, that's still running that solenoid like a machine gun. But nonetheless, 6 a second, who would ever want to count any faster than that? And so that surely ought to be adequate for most of our needs. Well, this is just illustrating where multi-channel analyzers started out, pretty far back the evolutionary chain. And they have, of course, gotten very much more sophisticated as time has gone on. This is an intermediate unit. This is a single-channel analyzer with a motor drive that moves an acceptance window continuously and sends the measured pulse rate to a strip chart recorder. So this can, again, scan through a spectrum and record the output as a strip chart display. And I'm actually have been in this business long enough to have used something very similar to this. So I have to confess I date back that far. Now, what's happened since then has been introducing greater degree of fidelity into the readout of sensors. In the 20th century, we were quite happy pulling off information using a single connector to the detector, to the output node, and reading things like pulse height spectra or timing information, and being quite happy with that. Today, we have a much greater capacity, and this is where I believe the great strides are coming now in the application of radiation sensors, and that is to have many readout nodes. And I'll show you an example of this in just a few minutes. Where now, instead of simply being content with pulse height information and timing information, we might like to learn a lot more, including information that can be carried by the time dependence of the pulse that is produced, its shape in time. Or if the sensor itself has non-idealities in it, it may be nonlinear in some way. One can, in fact, in many cases, correct for those non-idealities in the case where you have access to a more detailed set of data. And of course, the very important added application when you're trying to do imaging of some sort, you would like position information as well. So the tools that are now available in the electronic side of things have become very much more sophisticated. And that is where I believe the greatest strides are now coming in the measurement of radiation. A lot of this has been facilitated by so-called ASICs, application-specific integrated circuits. These are chips that are a centimeter or two on a side, and they provide absolutely astonishing degree of capability. This is largely a product of the world of high-energy particle physics, where very early on, that community was into reading out detectors with many, many multiple channels. And the only way to do that practically is to integrate that readout on a massively parallel chip. And these are commercially available at this point. Chips that have as many as 128 spectroscopic readout channels, each of which has a preamp, amplifier, shaping amp, and all the addressing capability needed to read out that data, all on a chip the size of your thumbnail. So this has become the revolution that is permitting a lot of new applications that were impossible as little as 5 or 10 years ago. Now this is not an ASIC, but a light sensor. And one of the presentations yesterday in the medical session, they mentioned of so-called silicon photomultipliers. It's a bad choice of name since it is not a vacuum tube as a photomultiplier tube is, but rather it's simply a silicon chip. And it has implemented on it a very fine two-dimensional array of avalanche photodiodes that are operated in what's called Geiger mode. And some of you may be familiar with standard avalanche photodiodes. They provide gain to the signal in a photodiode. If you raise voltage high enough on an avalanche photodiode, it enters what's called the Geiger region, where the output pulse saturates, just as it does in a Geiger tube. And from that point on, all pulses are the same size, regardless of what triggered it. But here you have a very fine array of tens of thousands of these cells of photodiodes. And the object now is going to be to trigger such a cell with a single photon. Well, that's possible. A single photon can come into one of these cells and trigger it. Well, that sends it into Geiger mode and produces a rather large size, large amplitude pulse. And if you simply connect together all of these cells and produce a signal that's the sum of all the cells, what you now get is a measure of how many cells have triggered. Each cell produces a pulse that is nearly identical in amplitude. And if you do for example, a pulse height spectrum with a very low level light source, you see something like a plot at the bottom, where you see one photon being recorded at a time. Here's 2 cells triggering at a time, 3 cells, 4 cells, and so on. So you're beginning to do what is really digital counting of photons. And in the readout scintillators, that is about as fundamental a piece of information as you can get. It is now the ideal piece of information that you would like to know from the scintillator. No complications of noise introduced by the amplification process, because you're simply counting digitally the number of photons. So this is, I think, again, a very powerful technique, not yet highly commercialized. They're still very much in the stage of development, but this is, I think, Very impressive plot from